My name is Ramon San Pedro. I'm a principal here at Stress Engineering Services in Houston, Texas. I am a mechanical engineer by training, and I've been a consulting engineer at Stress for coming up on 25 years this summer. And one of the areas I have worked on a lot is connections in general and bolted flange joints specifically. So to get started, let's go over a quick outline of the presentation for today. So I thought it'd be good to start with a definition so we all agree what we're actually talking about. I'll go over some of the applications, some design considerations specific to bolted joints, and then a little bit of what I think a proper system design process should look like. Then we'll get into the meat of the presentation on the mechanics of bolted joints. I'll introduce the topic. By then, we should have talked about how important bolt preload is. And I'll introduce that topic, which will actually be a topic of a webinar in the near future here. And then we'll wrap up with some thoughts. So starting with the definition, what I'd say, now when I say a bolted flange joint, the way I define them is that they are a deceptively simple means of providing a leak-tight connection between two parts of a pressurized system. They are by definition an interface between parts of a system or even between systems. So just for that reason, they deserve special attention, since in my experience, interfaces are so often the source of trouble. By the end of this presentation, you will understand why I say that their simplicity is deceptive. So looking at the components of a bolted flange joint, you can see they're on the screen. So the physical components are obvious. We have the flanges, the gasket, the bolting, but there is a fourth and highly critical component to a successful application of a bolted flange joint, and that is the assembler. Studies have shown that the single most significant factor in producing a properly assembled and reliable bolted flange joint is not the design, the material selection, the gasket type, the preload method, or the procedure used, but the knowledge, training, and ability of the person actually making the connection. So proper controls must be exercised in the selection and application of all four of these elements to attain a joint that is fit for purpose. Going over some of the applications, bolted flange joints are really ubiquitous in the energy industry, from upstream to downstream and in renewables, but they are also used in every other industry, from mining to aerospace and consumer products to medical devices. Since bolted joints allow for the assembly, disassembly, and reassembly, they are often the preferred method for connection when access for cleaning, inspection, modification, or replacement of components is required. The area where I have practiced much of my career and developed a deep knowledge of bolted flange joints is in the offshore drilling and production systems. And these systems, flanges can be found everywhere. Drilling risers, for example, are most often connected by bolted connections, such as those shown on the right. And the lower marine riser package, or LMRP, and the blowout preventer, or BOP stack, as shown in the middle, those could really be described as an assembly of components connected by bolted flange joints. And then the drilling, storage, and production systems on the top sides with pumps, tanks, and piping are also full of flange connections. But bolted flange joints are also indispensable in aircraft and space systems, for example. From the largest aircraft engine ever built, shown on the upper left, to the rocket engine that power the space shuttle and will power the heavy lift space launch system, and the systems that fuel these rockets, bolted joints are everywhere. Yeah, and I know what you're thinking, that only a flange guy would show you a picture with a bolted connection in the foreground and the rocket in the background, but I guess that's who I am. So bolted flange joints come in many shapes and sizes. Here we see applications in high pressure systems, in wellheads and in pipelines, in process equipment, and even at the base of a wind turbine tower. Standard flanges can range from a couple of inches in diameter to several feet in diameter, and wind tower bases like the one shown can be over 25 feet in diameter, but still the same basic principles apply to all of them. There are also many different styles of flange facings, like some of the ones shown on the left. Then bolt sizes can range from a fraction of an inch to several inches in diameter, and the number of bolts in a single connection can be as few as 4 or more than 60. And those example bolts just happened to be in my office, so I took a quick picture. And finally, gaskets can also be found in a wide range of styles and materials, depending on the application, as those shown on the right. Okay, so before getting into the details of bolted joint mechanics, and I promise we will, let's quickly discuss the design process that it applies to these assemblies. This is a list of design considerations for a bolted joint. As you can see, there are many interdependent factors to be considered. They may not all be applicable to every situation, but the more critical the application is, then the more critical it is to ensure the integrity of the connection. More of these factors, and perhaps others, will need to be considered. Some, like flange stress and bolt stress under pressure, tension, and bending loads, determine the static strength capacity of the assembly. However, static strength is usually not the only consideration, since flange rigidity, or how much the flanges rotate, and bolt spacing can affect or do affect the contact pressure distribution on the gasket and thus sealability. And the bolt preload, as we'll learn in this presentation, is critical in preventing flange separation, which helps ensure sealability and significantly improves fatigue performance. And finally, but no less critical, is material selection of all the components to assure adequate performance in handling the contained fluids, as well as external environmental effects. And really, many design guidelines, like the work of Eichenberg and the Taylor Forge manual, and things like what's on the screen right now, have been around and used successfully for decades. And like this graphic shows, there are many seemingly small details to consider, but many often get overlooked. So I'll just give you a moment to look at the list, and it gets quite extensive of all the things that you need to consider on a bolted joint. And other decades-old design rules seem to be rediscovered by each new generation. If, like me, you have been involved in deepwater drilling systems over the last decade or so, you may know that issues highlighted in this slide, like limiting the hardness of bolts and the potentially negative effects of coatings, have resurfaced, causing failures, millions of dollars in expenses and lost revenue, and increased regulatory oversight. So talking about the design process overall, with so many factors to consider in the design, assembly, and operation of bolted flange joint assemblies, which in turns are usually part of a larger system, it is my opinion that it is essential to approach the design process in a systematic and comprehensive way. Such an approach to design consists of the 4 general elements shown. So, performing a risk assessment, considering the entire life cycle of the assembly, taking a systems approach, and then developing and implementing mitigation strategies. So let's just take a quick look at each one of these. So risk assessment, formal risk assessment provides a means of ensuring that all interfaces are considered and all relevant failure modes are identified. The risk assessment process, whether it be a HACCP, a FAMICA, or a fault tree analysis, or some other method, should be comprehensive, identify risk, causes, frequencies of occurrences, consequences, and then appropriate mitigation strategies. It should conform to a formalized process and must be a team effort that includes a wide range of disciplines and experiences. So ultimately, components and failure modes considered critical must be identified and dealt with. And good designs rely on life cycle approach to categorize potential failure modes throughout the lifetime of the system, starting with a good basis of design and definition of technical and functional requirements. Then the design process itself takes place along with the definition of quality requirements. All of this taking into account all subsequent phases of the life cycle, as shown here. So I believe that designs are successful when they consider each and every phase of the life cycle, and product integrity is compromised when one or more of these areas are incomplete, misunderstood, or misapplied. And getting into a systems level approach, it must be taken in the design and manufacturing of the bolted flange joint itself and of it as part of a larger system. Bolted flange joints are often where a code break happens, or organizational responsibility changes, or even actual ownership of the equipment changes hands. So all parties should be involved in the system design process. After life and function requirements have been established and failure modes have been identified, this must be addressed by things like material selection, design verification, and validation testing. It is also beneficial, if not required, to monitor the inputs like pressure, temperature, and loads, for example, and the outputs such as strains and displacements for the given design in order to update the requirements and ensure system integrity. And after you have identified risk and causes and failure modes, you should consider how to mitigate against them. So each of the outer bubbles shown in this graphic is a way to do that. Note that here procedures are listed as a mitigation against some failure modes, and that will become particularly relevant when it comes to the assembly of bolted flange joints. So now getting into the meat of the topic here, this little animation, and I believe you see it moving here. The animation shows the basic components of a bolted joint, the bolt with, or a stud in this case, with the nuts, and the plates being joined together. And that we will refer to as the joint members or the grip. So you may hear me say the grip, so that's what I mean. So here the animation starts in the initial position with no loads and show how the joint members are compressed during the preloading process. Here the displacements are greatly exaggerated, so you can actually see what's happening. Then a separating force, that is a force trying to pull the two plates apart, is then introduced, which reduces the compression in the plates until they ultimately separate in this example. Okay, so here's a simple model of the mechanics of this problem. So basically a bolted joint consists of two springs in parallel. One spring is the bolt and the other spring is the grip. So here on the left-hand side, we're showing what's going on at preload. So when you're preloading a bolted joint, the bolt spring goes into tension and the grip spring, which is a compression load path, goes into compression. One thing that I have found really helpful in understanding the situation and to always keep in mind is that at preload, the forces are equal in magnitude and the displacements of the two springs are different. So that can be expressed by the simple equations at the bottom, that the force in the bolt is positive, it is in tension, and it is equal to the preload force that was applied. And the force in the grip has the same magnitude, but it's negative because it's in compression. Then looking at the right-hand side of the graphic, now when we apply an external load, which we define as P here, when you apply the external load, which is trying to separate the clamps after the plates after they have been preloaded, then the grip spring loses some of its compression. So it's losing some of the preload. And the bolt spring gains additional tension. So the rule to keep in mind here is that under external load after preload, the displacements are equal in magnitude, but the forces are different. So that can be expressed by the equation shown on the lower right. So the force in the bolt is equal to the initial force, the preload or F sub I, plus some fraction of the external load that was applied. And that fraction here is the quantity C. The force in the grip is equal to the initial compression, which is again F sub I, but you're losing compression by some factor. So it's actually the remainder of the applied load goes into relieving the compression in the grip. And that quantity C is the stiffness ratio between the bolts and the grip. So for these equations, the stiffness ratio is expressed as the stiffness of the bolt divided by the total stiffness, the sum of the bolts and the grip. So we need to know, to be able to solve those equations, and we need to know the stiffness of the system. So I thought we would start with what I call the easy one. Sorry about that, which I can put in quotes. So I joke that if you're a mechanical engineer, you have probably known this equation since kindergarten, but the stiffness of a bar is equal to AE over L, the area times the Young's modulus divided by the length. No, that seems pretty easy enough, but the only problem with that equation is that we don't know what A, E, or L really are. So A is equal, is it really equal to the root area or the stress area or some other area? What if we have a shank that's not threaded, but then you have a threaded portion and maybe some other features, changes in diameter? With all of these factors, or even just looking at root area versus stress area, you could easily be off by 3 to 6%, depending on the size of the bolt. Now, the elastic modulus, it's some property of the material, that should be really easy. And again, we all know that's 30 million PSI, right? Well, it could be 28, it could be 31. So again, you could easily be off by 3 to 5%. And again, I'm only talking about steel there. If it's different material, then it may vary even more. And then one that gets even a little harder in our simple equation is what is the effective length of the bolt? So if you have a stud going into a nut, how much of that length in the nut should be considered? Is it 1/2 diameter? Is it 1/3 diameter? Is it something else? What if one side of the connection is a blind hole? Again, how much of that length of the stud goes into the effective length? And then you also have deflections between the threads in the stud and the nut. So how do they come into play? So again, easily you could be off by 5 to 10% or more just on the effective length. So really altogether, your estimate of the easy one, the bolt, could be off by 10 to 20%. So that's getting to be a big number. So then we look at the stiffness of the grip, and I show one example there on the right in the graphic. So the equations now can get ugly pretty quick. But again, it's a stiffness we need to know if we want to understand the behavior of the joint. So here, I mean, one solution you find in textbooks is you look at the frustum of a hollow cone, as shown there, and that's the equation for it. So you can come up with an estimate. Now, if we do some FEA, like shown on the lower graphic, it tells you that the behavior pretty much agrees with that. But then again, what if your geometry is even more complicated than these simple examples, right? Again, your estimate for the stiffness of the grip could be off by quite a large amount. So now let's look at the load paths. So now let me start there again. Okay, so look at the load path. If we're applying on a, did I go too far? Yeah, there we go. Sorry about that. So load paths on makeup. So if we look at the left-hand side, and this is an API flange, we look at the left-hand side under compression, that load path, the stud is going into tension, and you have then putting compression, the nuts are putting compression into the flanges. That load is going at the beginning for this kind of connection, going only through the gasket. But then again, depending on the type of gasket, your flanges may come face to face, and now you have the same tension load path in the bolt. But then you have two different load paths on the compression side and the grip. Part of the load is going through the gasket, part of the load is going through the flanges. And again, as I showed earlier, you could have different facings, different gaskets, and that compression load path could have many different configurations. Now looking at the load path when we are under external load, here we have, again, two different situations. The one on the left is if you have no preload at all, then the only load path available for that tension is to go right through the stud. But if you had a preload, then now you have two different load paths. So one load path is, again, going through the bolt. So some portion of the load goes into putting the bolt in additional tension, but some other load goes into relieving the preload in the compression load path, relieving the compression in the grip. And again, that is two springs in parallel, and the ratio of the forces going into the stud and going into relieving the preload is a function of that stiffness ratio. So again, I show you this graphic here on this slide as a reminder. So it's a quick review. Now, if we look at preload at the left, we have two springs in parallel. The bolt spring goes into tension. The grip goes into compression. and the forces are equal in magnitude and in opposite signs, and the displacements are different. Now we have it under preload and we apply an external load. The grip spring loses some compression, so it's losing preload. The bolt spring gains some tension, and the displacements are equal in magnitude, but the forces are different. And then there I repeat the equations, and again we have that stiffness ratio C, the ratio of the bolt stiffness to the total stiffness. But now, by looking at this little system of equations, which again is simple enough, I can actually predict when flange separation is going to happen. So I have flange separation when the compression force in my grip is equal to 0. So if I solve for that, it's when the portion of the external load that goes into the grip, which is P times 1 minus C, is equal to my initial preload. So that is how I can now predict when separation is going to occur. So using that equation, then I can actually calculate a safety factor against flange separation. So that's the equation shown in the middle of the slide here. So the safety factor is my initial preload divided by that quantity P times 1 minus C, which is a proportion of the external load going into the grip. So these are two identical systems, and they are identical because the stiffness ratio is the same. So C is equal to 0.1 in both cases. So here 10% of the load would go into the bolts, which is kind of a typical number. The external load is also identical. So P is equal to 100 in both cases, but the preload is different. So on the left, I'm putting a preload of 150 units of force. On the right, I'm putting a preload of only 70 units of force. So for identical systems with different preload, on the left-hand side, my safety factor against flange separation is 1.7, so I don't expect it to separate. On the right-hand side, with less preload, my safety factor against flange separation is 0.8, so I do expect it to separate. So the graphs show what the behavior of each system is. So if sufficient preload is applied, as shown on the left, only a small percentage of the load goes into the bolts, and the tension in the bolts goes up, which is that dark blue line on top. And the compression in the grip goes down. So, but the flange faces here remain in contact. And here the externally applied load is that black dashed line. So external load goes up, the compression in the grip goes down, the tension in the bolt goes up, but the system stays together, no separation. So that's great. However, if preload is insufficient, as shown on the right, the preload is overcome after some load, and after that point, all of the applied load has been taken by the bolts. So here you see that initially the curves look the same as the curves on the left. A small portion of the load is going into the bolts, the rest of it is going into the grip. But at the point shown as flange separation, the grip loses all the load, so the compression force is 0. The flanges separate or the plates separate, and now all of the load is going into the bolts. And you can tell that because the slope of my bolt force line is equal to the slope, and actually the magnitude of the force is equal to the applied external force, which is the dashed line. But if you're familiar with this, or you may have noticed that now we have two conflicting requirements. Now, for my design, should the bolts be stiff or should they be compliant? Or do I want my bolt stiffness ratio to be high or to be low? So really the conflict is that to protect against flange separation, you would want the stiffness ratio to be high. So you would want relatively stiff bolts and a relatively compliant grip so that more of the load goes into the bolts and it protects your preload on the grip. But to protect the bolts from excessive loading, ultimately, and from fluctuating loads that would cause fatigue, then you want the stiffness ratio to be low. So you would want relatively compliant bolts and relatively stiff grip. So really, history has shown us and engineering principles show us that really the best designs will be the latter. You usually will want a relatively compliant bolt and a relatively stiff grip. But then you need to make sure you have sufficient bolting to take the load and sufficient preload upright to protect against flange separation from the design loads. Okay, so I think it's time for a reality check. So the little springs are cute and the equations are relatively simple, but it's sad how bolted flange joints really work. So the animation here, get it going again. It's showing you an FEA of an API flange. Um, so it shows that it turns out that case. Turns out that it is true. The parallel spring model for a single bolted joint is a very good representation of the actual behavior of a flange. If, and that's a big if, you know the stiffness of the components. So we can simulate the system in FEA, or we can actually prove it by doing a full-scale test as shown on the right. And we can even compare the two. And I was also going to point out something I haven't brought up, and it's another one of those design considerations for further discussion later, is if you notice on the FEA there, the bolts are actually seeing some bending shown by the red on the inside. So that has to do with the flange rigidity, which is one of the design considerations I mentioned early on. So this is what an FEA like the one shown there will show us. So I reinserted the plot of the system that doesn't have enough preload and will separate to show that the simple model and the FEA are in really good in agreement. So again, the dashed line is the applied load. The green line here is the bolt. So as we apply external load, the bolt picks up a little bit of the load. And here our compression path has actually two paths. So there's a path through the gasket and a path through the flange faces. So I'm showing those two separately there. But again, ultimately, because we don't have enough preload, the flange faces and the gasket separate, and all of the load is going into the bolts. And then we can even compare our FEA to some physical testing, as shown here. So in this example, 6 of the 24 bolts in this assembly were instrumented with strain gauges so that the bolt forces could be measured directly. The load per bolt predicted by the FEA is represented by the solid red line. Each of the 6 measurements is shown as a dashed line. So the actual behavior here matches the model prediction very well. So the separation load is predicted fairly accurately, and the behavior before and after separation isn't really the agreement. But as always is the case with experiments, you can see that there's some scatter among the 6 bolts. Particularly, you may also notice on the left-hand side that there is scatter in the initial bolt forces before any external tension is applied. So that is an indication of variability in the preload applied to the individual bolts. So let's talk about that. So as we have shown, I think I've proven to you that achieving the correct bolt preload in a bolted joint is essential. And traditionally, in the vast majority of applications to this day, the torque has been used to apply the preload to the bolting. So that leads us to another deceptively simple question. What is the correct torque? So let's take a quick look at some of the common answers. And here I have inserted a torque table. This one's taken from API spec 6A. I'm sure many of you are familiar with. So that is shown on the left. And a typical equation using a torque factor K is shown on the right. So you will notice that the determination of the required torque to achieve a desired preload in the bolts is completely and totally dependent on knowing the correct coefficient of friction to use. So a lot of issues arise here. Now, do I really know the coefficient of friction in my bolts and nuts and the flange faces? Do I know that for a given surface finish, with or without coatings, for my lubricant? Does the assembler in the field or in my shop know any of this? Do they know that it matters, or do they even care? And is that coefficient of friction the same on day one as a year later? Is it the same in cold weather? Is it the same for the first time I bolt this up compared to the 20th time I bolt this up? And looking at the 6A table, many times I've been told, well, that's what we use. If we just look at a 1-inch bolt, there are 4 different torques shown there for a different target preload, either 40 KSI or 52.5 KSI, and then for 2 different coefficients of friction. So is the torque I need to apply to my 1-inch bolt 213 foot-pounds, or is it 474 foot-pounds? If I apply one or the other, I'm going to get very different results. And again, if I'm using the equation, it all depends on mu, which is my coefficient of friction. So again, if you have been in the business for a while, you know that there will be an endless number of vendors telling you that they have invented a better mousetrap, right? So some will say, well, we have our torque wrenches are calibrated, and we know what we're doing. So you just put torque, and we know what preload you're putting on those studs. Or they may offer you something like a load disc washer or some other kind of load indicating washer, and then the wrenches are concentric, so they take out some of the side loads, so we know what load we're putting in the studs. Or they may offer you something like a rotobolt, load indicating bolt, so there the bolt itself tells you what load it's experiencing. Or they may say, forget torque and you need to go to stud tensioners, and even better, use stud tensioners with UT elongation gauges, and we know what load we're putting on the studs. Or you can go to the one on the far right, which is a super nut. And because they'll tell you we control all those surfaces and we're actually reducing the amount of torque you need so we can control it better. Now the counter argument would be now you've gone from not knowing the torque in one threaded connection to not knowing the torque in 8 smaller threaded connections. But really all of these contraptions are all based on sound engineering principles. And they all have advantages and disadvantages. And in my opinion, none of them on their own is the complete answer. So talking about bolt preload. So for critical bolted connections, now you need to know the preload. First, you need to know the preload you're targeting, and you need to know the preload you have. So in my years of experience, I've developed some approaches to this. So one is determining what preload is actually required. You can use some simple models to model your joint and then calculate a safety factor against flange separation, and you come up with a preload and you know your external loads, or you do final element analysis, or you use some other method. But first, you need to know what preload you actually need. Then my recommendation would be to use the actual connection or to physically simulate the joint to perform makeup trials. So actually go make it up. And while you're doing that, you make sure the load being generated in the bolts using strain gauges on the bolts. And you can do that to account what preload you're putting initially, and then also what preload you may be losing in the bolts due to relaxation and other effects. Generally, I would say tensioners are better than wrenches, but they're far from perfect. And when you use stud tensioners, you get into issues of running down the nut and how far you run it down, how you run it down, and you run into a lot of issues with relaxation after the initial makeup. My further recommendation would be to actually measure the elongation required to generate the desired load. So you can use ultrasonics, or you can use old-fashioned calipers if both ends are accessible, or you can use some other reliable means. And again, you need to repeat the experiment sufficiently to really establish the variability of all of these operations and your results. And then when you're making the makeup on the actual assembly in the field or in your shop, then again measure the elongation, compare it to what you had determined the elongation was required, and then you can do that at initial bolt up and then during operation. Throughout the lifetime, you can use it as a QA check, an inspection procedure, and then last but definitely not least is use written procedures for all of this. Don't just tell someone go make it up. Use the table in the back of 6A. So after you have done all of this, and you have taken care of flange rigidity and rotations and your bolts and the makeup and all of these things, you thought about the bolt spacing and looked at the stress and really worked out in your preload method, and you determine if your flange is separate or not, and you pick the right materials. you did all the work you needed to do to know what the external loads are, and you have looked at fatigue, have you ensured a leak tight connection? And the answer is not necessarily. So my suggestion is you really need to test it, and you need to work with gasket suppliers and work that out. But really, sealability is a topic for another day. But there are a lot of resources out there available to you. So I will leave you with a list of those resources. There are many others. I mentioned the Taylor Forge, and I mentioned Eichenberg's, and it's a lot of good resources on bolting. So here I show some of the ones most used in oil and gas, like API 6A and 6AF, 6AF2, and 20E and 20F specifications for bolting. Some studies on sealability. There are SME PCC1 and military and aerospace standards and specs. And there's a lot of other studies out there by the Welding Research Council and PVRC. And of course, now you can also reach out to us out here at Stress Engineering. And on ASME PCC1, that is on bolted procedures. So again, I would encourage you to stay tuned, and we'll be announcing a follow-on webinar to this one that will talk about bolting procedures and bolting more specifically. So with that, again, I thank you for joining us today.